Hello students, welcome back to my discussion on the time value of money teaching notes prepared for the Spiceland 7th edition from chapter 6. In this short podcast, I'm going to keep it as short as I can, I would like to talk to you about the future value of an annuity and the future value of an annuity due. I am about on page 331 of your book, and the first thing I would like to have you do is answer the question, what is an annuity? And the answer is an annuity is nothing more than an equal stream of payments. In order to use charts and present value functions without making some alterations, there are some rules you need to pay attention to. If you want to use the tables, you need to have equal payments, equal time periods, and a constant rate of interest. Should any of these break down, there are ways you can solve it, but we're going to have to learn techniques for that. An ordinary annuity is when a payment is assumed to be made at the end of the accounting period, and an annuity due is when a payment is assumed to be made at the beginning of the accounting period. Once again, I'm going to state I think the best way to really understand time value of money is to understand the chart, so I spend a little time with this concept. Let's start with future value of an annuity. I'm on page 332 in your book. On a future value of an annuity, there'd be an equal payment stream. And you could value them several ways. In our first way, I'd say you could do it using table 1 and add them up. Watch this with me. Table 1, interest factors, are being used here. So I'm going to make a payment of $1,000 at the end of each year for 4 years. This first payment will be made and it will be invested. It'll be made on the last day and it'll be invested for 3 periods. So if you go to table 1 and grab n equals 3, I equals 10, you get this interest factor. Times it by 1,000 and you get this amount. The second payment's $1,000 and it will be for 2 periods at 10%. That interest factor is 1.21 and it will equal 1,210. This third payment's $1,000 and it will be invested for only 1 period at 10%, so it's times the interest factor from table 1, 1.10, and this last payment will still be made, but it will be made on the last day of the 4th period. So we'll put a 1 here because we need to get credit for making the payment, but we won't inflate it for any interest factor. Total the interest factors, and it's 4.641. Total the amounts, and it's 4,641. And you could trace this number to table 3. Table 3 is an accumulation of the table 1 amount. So here's a cut and paste from table 3, and if you go to 10% and 4 periods, you'll see that those two numbers in fact do agree. The formula for using the interest table is to take the annuity amount and times it by a future value of an annuity due interest factor. In our case, n equals 4 and I equals 10%. Take the 1,000 times the 4.641 interest factor from table 3, and you could say the future value of the amount, $1,000 made as a payment at the end of each year for 4 years, would be 4,641. So one way to answer this would be to do the interest table. Very easy, yes? Another way would be to make a fund accumulation schedule. We'll do that one in a minute. And then the final way would be to use your time value of money calculator. Clear out the registers, enter an annuity of $1,000. If you have a Texas Instrument, you probably have to enter this in as a negative amount, so minus 1,000. 4 years, 10%, and solve for the future value. And you should get 4,641. If by chance you don't get this number, practice with your calculator until you do. You can always download instructions on how to use it on the internet. I would like you to be able to use future value interest tables, table 3, and your calculator to solve these kind of problems. So then you could say table 3 is a summary of table 1. That's cool. Let's check. I grab the table 3 interest table and placed it here for you. And then I went to table 1 and grabbed some interest factors. So if it's 3 years and 12%, I'm going to grab an interest factor for n equals 2, I equals 12, n equals 1, I equals 12, and then just add 1 to that because we've already decided there's one more payment than there is interest period. Add those up, and it comes out to be 3.3744. If you go to table 3, you can check this interest factor and see indeed at 12% in 3 years it is that amount. So you could say that table 3 was built on summing table 1. Some poor fool who made table 1 and then the reciprocal of table 2 had to add all the table 1 factors together to make table 3. And it is an interest factor. So since it's an interest factor, you can use it on any amount of dollars to get your answer. You can answer the question, how much will $5,000 a year deposited at the end of each year grow to be at the end of 3 years if you earn 12%? Remember, here's that interest factor. First, you could solve that by table 1 and the formula. Take the annuity times the future value interest factor, where n equals 3 and I equals 12%, which is 3.3744. 5,000 times that would be 16,872. Now let's do that by using a fund accumulation schedule, which I just erased because I didn't want you to see that yet. At the beginning of the period, you have no money, and at the end of the period, you deposit $5,000. You won't get any interest on that for the first period because you deposited it at the end, so your ending balance will be $5,000. For the second period, you'll earn 12% on that $5,000. 12 times percent of $5,000, $600. Maybe I should get my 6 in there, huh? And then at the end of the period, you'll come in and make another payment. It won't get any interest on it because you make it at the end. So you have your beginning amount, the payment you made, the interest on your ending balance for the last period, and that will equal 10,600. 5 plus 5 plus the 600. 10,600 is going to be invested for the entire year, and you're going to earn interest on that. So you will earn $1,272 on that interest for the money you have invested all year. On the last day, you'll come in and you'll make a $5,000 interest payment. Now you'll have $10,600 plus the $5,000 you made at the end, plus the interest you earned on the $10,600 of $1,272, and your total will be $16,872. I want you to notice you have 3 interest periods, 3 payments, and 2 interest periods, and it totals $16,872. Your resulting journal entries would be simple. You record the cash payment or the deposit at the end of the first year, record the second one at the end of the second year, and pick up interest on the balance in your account for the year. Record the third payment, pick up interest, which we calculated right here, on your balance for the year, and you would end up with $16,872. The key to doing this well is to remember the payments are made at the end, and so the current payment doesn't get any interest on it. Let's focus on that a little bit. I'll get rid of that blank space there. How many payments do you see on the accumulation schedule we just made? 1, 2, 3. So 3 payments. How many interest periods? 2 interest periods. What's the total interest on this one? Well, the total interest is going to be $1,872 because the payments were made at the end. And what's the total principal? The total principal on this is going to be $15,000. Now let's see if you can use your time value of money calculator to solve this. Clear out the registers, enter the $1,000 annuity as a payment, as a negative number, put in 3 payments, put in 3 periods, put in or 12% interest and solve with your time value of money calculator. And do this until you get 16,872. Go ahead and download your instruction manual from the internet if you need a little help. And once you've read this section on future value annuities, please read page 332 to 335. Welcome back, and I'm going to launch right into a discussion on future value of annuity due. This is information presented on page 333, and I'm doing these two topics, future value of an annuity and annuity due, together. The question I want to ask you is, how much will your $5,000, if deposited at the beginning of the year, grow to be at the end of the 3 years if you can earn 12%? Since this is a future value of an annuity due, payments made at the beginning, you're going to have to go to Table 5, and you could get your answer from Table 5. You would go to Table 5 and go down to 12% in 3 periods and find the interest factor, 3.77933. 5,000 times this interest factor for an annuity due will give you 18,897. So that would be one way to solve this very fast. A slower way to solve this would be to make a fund accumulation schedule. I want you to notice that I've added an extra column, the balance for interest column. Now watch what happens on this schedule. You start the period with 0. You make a period of 5,000 at the beginning. So you're going to earn interest on that the whole period. 5,000 times 12%, 600. And at the end of that year, you're at 5,600. The beginning of the next year, you have 5,600, and on that very day, put another 5,000. And it sits there for the whole year. So you have interest accumulating on 10,600, the balance of those two for the whole year. 12% of that is 1,272. So your ending balance would be 11,872. That would be your beginning balance at the beginning of the 3rd year. The next day, or that very day, you'd put in another 5,000 and let it sit for a year. So you would have 16,872 invested for the whole year. Times that by 12%, and you'll get interest of 2,025 on that balance, leaving you a balance of 18,897 for an annuity where you're exactly the same as the previous annuity we looked at, except the difference is you're making the payments at the beginning of the year instead of the end. The resulting journal entries would be similar to what we looked at on our last problem, except more interest. Make your deposit on the first day of the period, pick up interest at the end. Make your deposit on the first day of the period, pick up your interest at the end. Make your deposit on the first day of the period, pick up your interest at the end. So, let's back up a little. So I repeated our fund accumulation schedule here for you, and I'm going to make a comparison with the regular annuity. How many payments were made? In both cases, 3. But how many interest periods are there on annuity due? And for regular annuity, it was 2. But notice for an annuity due, there's 3. There's interest on all 3. And total interest won't be 1,872 in our example. No, if I can get to it, it will be $3,897. How much total principal? Still $15,000. So why is there more interest when deposits are made at the beginning? And the answer is there's as many interest periods as there are payments on the future value of an annuity due. It has one more interest period. Think of the big difference it made. On the annuity due, when payments were made at the beginning, we had $3,897. When I go up and look at the regular annuity, where there's only payments made at the end and only 2 interest periods, total earnings are only $1,872. Quite a difference. Let's do a quick diagram of this. I'll use an example of $1,000 made, 4 payments at 10%, an easy number. $4,000 when payments are made at the end of 4 periods, 1, 2, 3, and 4, where the first payment has 3 interest periods, the second payment 2, the first one, and the last none. From Table 3 shows you an interest factor from Table 3, n equals 4 and I equals 10 of 4.6410. Compare that to an annuity due, where payments are made at the beginning. The first payment has 4 interest periods, the second 3, the third 2, and the last one 1. There are as many interest periods as there are payments, and the interest factor for this becomes 5.1051. It is a big interest. If you take Table 3, 4.6410, and increase it by 10%, 1.10, it becomes exactly the Table 5 number. So I have hoped I impressed upon you that the difference between an annuity and annuity due is an annuity due has 1 extra interest period for each payment when it comes to future value. Go ahead now and read pages 333 and 334. There's not a lot there, and that will summarize what we've learned in this section. Thank you for joining me.